Continuing on with learning target 2D, in class we started talking about this section and we approached it from a graph perspective to determine if a function was differentiable or not. Remember, for a function to be differentiable, it means the derivative does exist. Those phrasings mean the same thing. In this video, we're going to focus on what happens if a piecewise function is differentiable or if a piecewise function is not differentiable. So the definition for a piecewise function to be differentiable, if we have a function y, which is defined to be f of x if x is less than or equal to a, or g of x if x is greater than a, then y prime has two options. Y prime is going to be equal to f prime if x is less than a, or g prime if x is greater than a, or the other option would be the best case, would be that y prime is equal to f prime when x is less than or equal to a, so that equals 2 bar that we had to begin with is still there, or g prime is or y equals g prime when x is greater than a. In this first case here, we do not have that equals 2 bar back, which means that this function y is not differentiable at x equals a. In that second case, because that equals 2 bar gets to go back, it would mean that y is differentiable at x equals a, meaning y prime does exist. Now this equals 2 bar didn't have to always go with the top function here. It could have gone with the bottom function, but for the sake of simplicity, I just had it typed out one way in your notes. Now to decide which scenario we get for y prime, we have to first determine if y is differentiable at a specifically, because that's the difference between these two. For the less than and the greater than case, those derivatives still hold because we are assuming that f of x and g of x themselves are already differentiable. So their derivatives each exist, and they exist on the less than or the greater than interval. But what we're curious about and what the interesting part of this is do they actually meet up and we get the equals 2 bar back? Now for that to happen, y would have to be differentiable at x equals a specifically. We have to have two things to be true for that. We know that differentiability implies continuity, so if I have a function that's differentiable, that function first needed to be continuous, so we will check and see if y is continuous at x equals a. Why don't you guys pause the video and write down what would have to be true for y to be continuous at x equals a. It's a little refresher here from continuity from our last unit. For a function y to be differentiable, it would mean that the limit from the left and the right are both equal, and that also equals the function value there. The second thing we have to check is for the continuity on y prime. We know from looking from a graph perspective, if the derivative is completely continuous, specifically at this breakpoint x equals a, then what it means is that we would have that smooth curve there, so we have to check for the continuity on y prime as well. And if both of those things hold true, then our function is differentiable at x equals a, which would mean that we get to fall into the second case where the equals 2 bar gets to go back. If one or both of these fails, then we are in the first case where y prime is not differentiable at x equals a, and we would not get to put the equals 2 bar back. But what's important to notice is since f and g themselves are both differentiable, we get one of these two scenarios. We can still find y prime. The difference is if x equals a is not differentiable at that point, then we don't get the equals 2 bar back and we fall into this first case. But if we can satisfy both conditions here and y is differentiable at x equals a, then we get to put the equals 2 bar back. So let's look at our first example here. So we have let y equal this piecewise function where it's x squared plus 1 if x is greater than or equal to 0, and x cubed plus 1 if x is less than 0. Now we know each of these functions are differentiable since they are both polynomials, which are smooth curves. So I know that the derivative of x squared plus 1 exists, and the derivative of x cubed plus 1 also exists, which means for sure we're guaranteed this first case up here with the less than and the greater than sign. So the first thing I'm going to do is write that out. We know for sure that y prime is at least the derivatives of each when x is greater than 0 and when x is strictly less than 0. What we're unsure of is if I get to put the equals 2 bar back. And I should have mentioned this up above, but if both of those conditions hold and we get to put the equals 2 bar back, it would stick with the function that had it to begin with. So in our general definition up here, since f of x has the equals to bar, that f prime would get the equals to bar. It can't switch between the two functions. So what would the derivative of x squared plus 1 be? Take the derivative of that guy, we'll use the power rule. Derivative of x squared is going to be 2x, and then the derivative of plus 1 is going to go to 0. So my derivative for my top function here is 2x, and that's guaranteed at least when x is greater than 0. I'm not sure about that equals to bar yet. We have more to prove there. Now we can also take the derivative of x cubed plus 1. Again, we can use the power rule and we'll get 3x squared, and then we'll still have x is less than 0. For sure, we're at least at minimum guaranteed this for y prime. Now we have to determine if that equals to bar gets to go back or not on the 2x part of this function. Well, the first thing that would have to be true is that we have to make sure the original function is continuous. If the original function is not continuous, there is no way that the derivative is going to exist then at that breakpoint if the function is not continuous at that breakpoint to begin with. So let's start by checking the continuity on y. So we are going to check to see, if y is continuous. So one of the first things we're going to have to compute is the limit from the left and see if it equals the limit from the right. Why don't you guys pause the video and compute both of those limits for our original function y. Let's check those limits. So if I compute the limit as x approaches 0 from the left for our function y, we would be using the bottom function here, since that's x is less than 0 when we're to the left of 0. So I'm using the x cubed plus 1. I can do a direct substitution into that limit, and I would get 1, since I would end up with 0 cubed plus 1, so we would just get 1. Let's do the same thing for the limit to the right. Now if we're to the right of 0 for this function y, we're using the top function, since that's where x is greater than 0. So we're going to take the limit as x approaches 0 from the right of x squared plus 1. That can also be a direct substitution in, and we get 1 as well. Now we know from our last unit that just because the limit from the left equals the limit from the right does not necessarily mean that our function is continuous. We also have to compute the function value there. So we also have to think about at x equals 0, is that equal to these limits? So we need to compute that f of 0. Now we could rename this y, of course, f of x. So I'm computing f of 0 as the function value. We'll use the top function since that has the equals to bar. So we'll be substituting that into x squared plus 1. Now for proper notation, I would not want to write x squared plus 1. Since I'm calling this f of 0, I want to plug in 0 right away. So this is equal to 0 squared plus 1, which if we simplify down is also equal to 1. What all of this tells us, since the limit from the left equals the limit from the right equals the function value, that yes, our original function is continuous. So let's write all that out. So since the limit as x approaches 0 of y, or f of x, I'm going to stick with f of x, equals f of 0, then yes, our function y, which we're calling f of x, is continuous at x equals 0. I'm going to shorthand continuous here. So what we've proved so far is that the original function is continuous. That's the first thing that we have to check. Now this does not necessarily mean that the function is differentiable. Remember, just because a function is continuous does not imply that it is differentiable. That example that you always want to be keeping in the back of your mind is an absolute value graph. And we're actually going to go through that example algebraically using this in a couple examples. But the absolute value graph is continuous, but it is not differentiable at that corner. So the next thing we have to check is we have to check to see if y prime is continuous. Because if y prime is continuous and y is continuous, then I know that the original function y is differentiable. So we're going to check to see, if y prime is continuous specifically at x equals 0. I know it's continuous everywhere else. It's the breakpoint that we're curious about. So we're going to have to compute both the left and the right limit as well to start with on these. So we'll have to compute the limit as x approaches 0 from the left of y prime and the limit as x approaches 0 from the right of y prime. Remember, we have our y prime function. It's 2x if x is greater than 0 and 3x squared if x is less than 0. So why don't you guys pause the video and find both of those limits and we'll see what we get. So let's check these. If we're doing the limit as x approaches 0 from the left first, we want to use the bottom function here, that 3x squared. That can be a direct substitution as well, and we'll end up with 0 squared times 3, so I'll end up with 0. We can do the limit from the right. That will use that 2x function, which also can be a direct substitution. We'll get 2 times 0, so we'll end up with 0. So in this case, the limit from the left does equal the limit from the right. And since the equals to bar would get to go back with the top function, then this is enough to tell me that f prime, or that y prime, depending on which one we want to call it, f prime and y prime are equivalent, is continuous then at x equals 0. Now what that tells us overall is that since both functions, since the original function f of x and f prime, so I needed both of these to be continuous at our breakpoint, so since both of those guys are continuous at x equals 0, then what it tells me is that the derivative of f of x, which would equal f prime of x, using our notation, exists then at x equals 0. That's ultimately what's happening here. What that tells us then is that I get to put the equals to bar back with the function that it would match up with for the original guy. So I do get to put this equals to bar back for that top function, since both the original function y are our f of x, and because our y prime or our f prime, since they were both continuous. Our final answer here is this piecewise function, and as silly as it sounds, all of that work was necessary to prove that that equals to bar gets to go onto this function. We can't just write this as our final answer and kind of cross our fingers and hope, well, maybe this one gets the equals to bar, maybe it doesn't. I actually need to prove and show why that equals to bar gets to go back. So lots of work is required for these. They're similar to our problems where we proved if a function was continuous or not back from Unit 1 because of all the limits that we're checking in the function values. Let's look at example 4. So in example 4, we have the function y equals x cubed minus 1 if x is greater than or equal to 0, and x squared plus 1 if x is less than 0. And they want us to, again, find the derivative. So let's start by writing what we know so far. I know that x cubed minus 1 and x squared plus 1 are both differentiable. They're both polynomials, so each of their derivatives do exist, and I can find those using, in this case, the power rule for both of them. So in our top function, if I take the derivative there, the derivative of x cubed will be 3x squared, the minus 1 will drop out, and I know that for sure I'm at least guaranteed that x is going to be greater than 0. I can't put the equals to bar there necessarily. I'd have to prove and show that this function is differentiable at 0 first before that equals to bar can go there. Now for the bottom function, we have x squared plus 1. That also gets a power rule, and I get 2x, and that will hold true when x is less than 0. We have to now determine if that equals to bar gets to go back or not. If it does, it would only go with the top function since it came from the x cubed minus 1 to begin with. So the first thing we have to see is is y continuous? That's the first thing we're asking ourselves. So we have to compute the limit from the left, limit from the right, and the function value and see if those are all equal or not. So let's start with both limits. So let's compute the limit as x approaches 0 from the left for our function y, and the limit as x approaches 0 from the right for our function y. Why don't you guys pause the video and compute both of those limits and see what we get. So if we're doing the top, or the limit from the left here, as x approaches 0 from the left, we'd be using the bottom function since that's where x is less than 0. So we're using that x squared plus 1. That can be a direct substitution. I'll end up with 0 plus 1, so I'll just get positive 1. If we compute the limit from the right, I'll be taking the limit as x approaches 0 from the right. This time we're going to use the top function of x cubed minus 1, since that's where x is greater than 0, which matches up as we approach from the right-hand side. This can also be a direct sub. When we sub that in, we end up with 0 minus 1, so we end up with negative 1. Now what does this tell me if the limit from the left is equal to positive 1 and the limit from the right is equal to negative 1? Well, what this tells us is that since the limit as x approaches 0 from the left of our function y did not equal the limit as x approaches 0 from the right of our function y, that tells me that y is not continuous at x equals 0. I don't even need to compute the function value. The left and the right do not equal. On a graph, there'd be a jump discontinuity there since the left and the right are not agreeing. And that tells me that my original function y is not continuous at x equals 0. What that automatically implies is that if a function is not continuous, then a function is not differentiable. So since y is not continuous, then y is not differentiable. Oops. There we go. So since y is not continuous, y is not differentiable, which tells me that y prime does not exist at x equals 0. And I should have been specific up here. Y is differentiable at other places, but y is not differentiable specifically at x equals 0. So y prime does not exist at x equals 0. What that tells me in my answer then is I do not get to put the equals to bar back. My derivative only holds true for the less than and the greater than case, but no equals to bar gets to go back there. So we've seen through these two examples where we could have derivatives that exist at the breakpoint, like in example 3, since in that case both the original function and the derivative were continuous, so that means that equals to bar gets to go back. Or in example 4, in this case, since the original function was not continuous, then there is no way that the derivative can be continuous. Now the other case would be sometimes there are functions where the original function is continuous, but the derivative is not. And that could happen as well. And so it's important that even if you get that the original function y is continuous, that is not enough to say that the derivative is going to exist yet. We have to first prove or see if that derivative is continuous. So let's look at example 5. So example 5 says let f of x equal the absolute value of x. Is f of x differentiable at x equals 0? We want to support our answer algebraically and graphically. I'm going to start with the graphical approach over here. So from a graph, and we talked about this in class, the absolute value graph is our V-shape. It's that graph that it has that point where they connect at 0, 0. If I plot points, I'd have 0, 0. I'd have 1, 1 on here. I've had 2, 2. I'd also have negative 1, 1, since the absolute value of negative 1 is positive 1, negative 2, 2. All of those points keep going. So we have these two branches to this graph. They're each their own straight line, and they form together at the origin at 0, 0. Now we know from what we talked about in class that this graph is not differentiable at x equals 0 since there is a corner there, or a sharp turn on that graph. And graphically, when we're approaching to see if a function is differentiable, we need there to be a smooth curve or a smooth transition between any two parts of that graph. And since here we go from a straight line with a slope here of negative 1 to then another straight line with a slope of positive 1, there is no way to have a horizontal tangent line in between those since that is such a sharp turn or a corner right away. The other place that those could occur is if we have a cusp on the graph, which we talked about in class. That would be like a curve, two curved lines kind of coming together. That would also form, in that case, a cusp, or in this case, a corner. We ultimately need a nice smooth curve like any polynomial has, but in this case we are not differentiable at x equals 0 since there is a corner specifically at x equals 0. Now the rest of the function is differentiable along this branch with the positive slope and along the branch with the negative slope. All of that's differentiable, just not at the corner, so just not at 0 specifically. Now let's take a more algebraic approach to solve this. Well, to do that, I'm going to need to define the absolute value. We'd actually talked about this back in our first unit when we talked about some absolute value limits, but the absolute value of x is a piecewise function. It's x, if x is greater than or equal to 0, that's the first part of the piecewise function, or it's negative x if x is less than 0. And the reasoning behind that is we have to think about what the absolute value does. Now, the absolute value is the distance from the origin. It also makes all of our numbers positive. It's more of an elementary approach to the absolute value. Well, if I am in this top case where x is greater than or equal to 0, all of those numbers are already positive. So the stuff that I'm subbing into the absolute value, that x, is already positive, so there's nothing that the absolute values do. The numbers don't change there. That distance was already positive. But in the second case where x is less than 0, all of these numbers are negative. So what I'm substituting in here, this x, is a negative number, since x is less than 0. Well, to make a negative number into a positive number, I would multiply by a negative sign. So although negative x might look like a negative number overall, really it's a negative times a negative, so overall this value is going to be positive. Since remember that x that we're subbing in here in this case is less than 0. So negative times that negative value is going to give us a positive number overall. I think before we had looked at taking the absolute value of -2. By definition, that would be a negative times that -2, which gives us that overall positive number. So that's an example of what's happening down here in this bottom case. Well, we're trying to determine if f of x is differentiable at 0, which is the breakpoint for this piecewise function. Now we know from a graph perspective that it's not differentiable, so we need the algebra or this limit approach of continuity to back that up. Let's see what happens here. So if we take the limit from the original function, so we want to see, is f of x continuous? Is the original function continuous at x equals 0? Don't know why the pen's delaying so much. So let's see where this fails. It might fail for the original function. What I would have to do here is I'd have to take the limit as x approaches 0 from the left of our original function. So in that case, we would use the bottom part of this. So we'd be looking at the limit as x approaches 0 from the left of negative x. That can be a direct substitution in, and in that case I would just end up with 0. Technically I get -0, but there is not a difference between a negative or a positive 0. Now we can also do this as the limit as x approaches 0 from the right of this function. Now in that case we're using the top part of the piecewise function, which is just x. And if we substitute in 0 for that limit as well, we can do a direct sub and we get 0 as well. I could also check the function value. Let me fit it down here. So I could check f of 0, and in that case I would use the top function, so I would just get 0 out. What this tells us overall then is that yes, our original function f here of x is continuous. Which if I look on the graph, I can see that that graph is continuous. This is why it's so important to check to make sure that our potential derivative is also continuous. So I'm going to do that in green. Let's find what f prime would equal. So since both parts of this piecewise function themselves have a derivative, I can take the derivative of x, that'd be equal to 1. That will hold true when x is definitely greater than 0. If I take the derivative of the bottom function, that would be -1, and that holds true when x is less than 0. Now, we know that the original function is continuous, but we also know from the graph that the derivative should not exist at 0. So something has to fail here when we check if f prime is continuous. Specifically, we're checking that continuity at x equals 0. Well, why don't you guys compute the limit from the left on our derivative on f prime and the limit from the right. Let's see if those agree or not. Well, if we're doing the limit from the left, we would be using the bottom function here. So the limit as x approaches 0 from the left of -1. Well, the limit of any constant is just that constant itself, so I'll get -1. And if I do the limit from the right, then I'm taking the limit as x approaches 0 from the right of +1. Again, I'm just taking a constant, which will be equal to that value. Well, in this case, the limit from the left did not equal the limit from the right. So what that tells me then is that no, f prime is not continuous. Let me scroll down to get this to work better. And so since f prime is not continuous, it tells me that the derivative of f, which is f prime, cannot exist at x equals 0 then. So since f prime is not continuous, specifically at x equals 0, it is continuous everywhere else, but at x equals 0 it is not continuous, that tells me that the original function f is not differentiable then at x equals 0. So I hope I can fit the whole word. Yeah. Sorry, I don't know why the pen is acting up so much. There we go. So since f prime is not continuous at x equals 0, f is then not differentiable at x equals 0. And of course, this algebraic approach took a lot more work than us just being able to look at a graph and saying, oh no, since there's a corner there, my function cannot be differentiable. One thing I do want to make clear, this is a graph of the original function. This is a graph of f of x, that absolute value, not a graph of the derivative. But if we were to look at a graph of the derivative, what we would have here is we'd have a jump at x equals 0 since the limit from the left doesn't equal the limit from the right. And since there's that jump there, it means that that function value at 0 then does not exist. So in these three examples, we kind of saw the three cases. We saw when both the function, the original function, and the derivative are both continuous. Then it means the derivative exists at the breakpoint. That was in that first example, meaning the equals 2 bar gets to go back. In the second case, we saw what happens if the original function was not continuous, then automatically the derivative cannot exist there, so there's no equals 2 bar. And then in this last case that we just looked at, just because the original function is continuous does not mean the derivative is necessarily continuous, which is why it's so important that even if you get that the original function is continuous, you have to check and make sure to see if the derivative is continuous. And in some cases, the derivative is not continuous, which means if I was trying to find an answer for f prime of x in an equation, I would not get to put the equals 2 bar back. So here that we have of f prime of x, notice I have x is strictly greater than 0 and x is less than 0. There is no equals 2 bar since that derivative is not continuous, which means that the original function, there's no way for that to be differentiable at x equals 0. Okay, I want us to look at one more type of example here. So in example 6, we have, it says, it's a little different. It says find the coefficients a and b. So a and b are coefficients on this x squared and this constant term. So a and b are real numbers that we're looking for. So that f of x, this piecewise function here, is differentiable. Well, we get to work a little bit backwards here. They want us to find the two numbers so that this function is differentiable. So we get to assume here we're going to let f of x be differentiable. What that means then is we have to think about what are we given. If a function is differentiable, what do I know has to be true? What do you guys think? If a function is differentiable, what am I guaranteed to be true? Well, we're guaranteed two things. So we're talking about differentiability specifically at the breakpoint here. That would be the number in question. So this time at x equals 1. So if f of x is differentiable at x equals 1, then it tells me that f of x is automatically continuous at x equals 1. And it also tells me, and this is key, I need both things here, and I need to think about both things, that f prime of x is also continuous at x equals 1. I'm sorry, I have a typo there, not x equals 0. I was looking back at the prior example at x equals 1. So remember here our breakpoint this time is 1. So since f of x is differentiable at x equals 1, then I automatically know that f of x is first continuous at x equals 1, and that the derivative, f prime of x, is also continuous at x equals 1. So we get to take advantage of both of those facts. Let's start with the original function being continuous. So I'm going to start with this first thing here. If f of x is continuous, that means that the limit as x approaches 1 from the left of f of x has to equal the limit as x approaches 1 from the right of f of x. So we saw some similar problems to this back in Unit 1 when we dealt with continuity, and in those examples it said to find the single coefficient so that the function was continuous. And in that case, since we're assuming that, we get to start with the fact that if a function is continuous, the limit from the left has to equal the limit from the right. And we can compute both of these. So if we're computing 1 from the left, in this case we'd use the top function, which is ax squared plus minus b. That has to equal the limit as x approaches 1 from the right, which would be the 2x minus 1. Both of these can be solved by direct substitution. So if I substitute in 1 into the ax squared minus b, I'd end up with a minus b equals, if I substitute in 1 on the right limit, I would end up with 2 minus 1, which would give me a value of 1. So far I've got one equation that involves both a and b, but I can't solve this for either variable without knowing what the other one is. So that's why we also have to use the fact that f prime is also continuous. So if I know that f prime is continuous, well, let's first find f prime, because right now I don't have an equation for it. Well, I can take the derivative of each of these piecewise functions using the power rule. So the derivative of ax squared, a is just a scalar or coefficient on there, so it's going to go along for the ride. Derivative of x squared is going to be 2x, so I'll get a times 2x. Now, minus b, remember b is a number. The derivative of a number is going to be 0. So my derivative here is just a times 2x, and that will be true when x is less than 1. And then the derivative for the bottom function is just going to be 2, since the negative 1's derivative is also 0. And that will be true when x is greater than or equal to 0. I get that equals 2 bar there because f prime is continuous. So I know that that equals 2 bar goes there, because remember this function is differentiable. So let's compute the limits on both of these. We're going to compute the limit as x approaches 1 from the left for f prime of x. That has to equal the limit, oops, come on marker, as x approaches 1 from the right of f prime of x. Why don't you guys compute both of those limits and then let's check them. So for our limit as x approaches 1 from the left, we're going to use that top function, that a times 2x. I'm going to rewrite it as 2ax just because we usually put the number in front, equals the limit as x approaches 1 from the right of just 2. So what that tells me then, if I take the limit from the left, I can direct sub in. I'm direct subbing in 1 for x, so I'll end up with then 2 times a, technically times 1, equals, well, the limit as x approaches 1 from the right of 2 is just going to be equal to 2, since that's a constant. Here now I have an equation where I can actually solve for one of those variables, since I only have one variable. To get a by itself, I would divide both sides by 2, and I'll end up with a equals 1. So we were able to find one of those numbers so far, but I can use this value and substitute it into this other equation, and I would get 1 minus b equals 1. So to get that by itself, if I subtract the 1 over, I would get negative b, oops, it's not right into the prior problem. If I subtract that 1 over, I'm going to get negative b equals 0, but that's just the same thing as b equals 0 then. So we were able to solve for both of those both those coefficients a and b by taking advantage of the fact that they're letting us assume that my function is differentiable. And that is so powerful. That means that my function is continuous, and it means that the derivative is continuous. And so using both the fact that the original function is continuous and setting the left and the right limits equal to each other, and using the fact that my derivative is also continuous and setting those left and right limits equal to each other, we were able to get a system of equations here where we could solve for both a and b then. So in this video we went through kind of a more function algebraic approach to how can you determine if a piecewise function is differentiable or not. For that function to be differentiable, you have to check to see if the original function is continuous, and you have to check to make sure that the derivative is also continuous. If both of those hold, then you would get to put the equals 2 bar back in your equation for y prime. If one or both of those fail, then we would not get the equals 2 bar back in our equation for y prime. And we would be left with strictly less than and greater than inequalities. Then in this last example, we looked at kind of how can we take a backwards or a flipped approach to it, and if I assume that the function is differentiable, what information does that tell me, and how can I use that to find missing pieces of this function? So again, if a function is differentiable, we are automatically continuous. That is the biggest takeaway from this section. Differentiability implies continuity. And what that means is that both the original is continuous and the derivative in a piecewise function is also continuous at that breakpoint then.